Alright, let's solve another kind of problem then. Here's the problem we want to solve. A gas sample occupies 50.0 liters. Well, I hope we all know that's a volume. 50.0 liters. And the temperature is 13.5 degrees C. If a red flag isn't going up in your head, it should be. Think about it. Why do we need to change this? How do we need to change this? Why should a red flag or alarm bells be going off in your head about degrees C? And then we've got this other unit of measurement over here, 105 kPa. We said it in an earlier video, but just to make sure we're clear, if you can't figure out what dimension that measures, kPa measures pressure. P is 105 kPa. And it says, what volume should it occupy at these new things here at 750 K and 75.3 kPa? So we're changing the temperature to K, and we're changing this stuff here, which is pressure. We have a new temperature. That means we have a temperature 2, 750 K. And let's go ahead and put a decimal place right there and say that 0 is significant, okay? And then we've got a new pressure. Pressure 2 is 75.3 kPa. So if we've got a new temperature and new pressure, this is temperature 1 and pressure 1. It's asking what volume should it occupy. That means we have a new volume. Volume 2 we don't know. That makes this volume 1. So now what we need to do is we got two things to do. One, we have two different temperature units. We talked about that red flag or sirens going off in your head or bells going off in your head about this degrees C anyway. You cannot solve gas law problems using Celsius temperature. We've got to convert this to Kelvin. The way we do that is we take that 13.5 degrees C, we add that to the conversion amount, which is 273.15. We can see that there's an empty slot above the 5. And we add these together then. $286.65, but that empty slot above this 5 means that gets rounded off. So we're going to show an arrow to show we're rounding off, and we get 286.7 Kelvin. And this is also Kelvin. Okay? That's the value up here we want for this. So this is 286.7 Kelvin. Okay? That's the version of the temperature that we need. So let's look at our knowns and unknowns. Let's see, we've got volumes and temperatures and pressures that are changing. We look at our four equations that we looked at earlier, and this one has volume, temperature, and pressure changing. So that's the one we're going to use. P1 V1 over T1 equals P2 V2 over T2. Now we're going to plug in the known values. Make a list of knowns and unknowns. Make sure you got the right units here. Pick out the right equation and write it down. It's required that you write down the equation you need. Then we're going to substitute the values that we have. We have P1, 105 kPa. We have V1, 50.0 liters. We have T1. The version we must use is the Kelvin version, 286.7 Kelvin. On this side, we have a P2, 75.3 kPa. V2 we don't know, so we leave that in this form, V2. And I didn't leave myself enough room here. I'm going to have to rewrite this to make some more space. And then we have T2, 750 point decimal place, Kelvin. Okay. Now what I need to do is get this V2 by itself. It's the unknown. I want to get it by itself. I want to rewrite the problem down here because I need some space on both sides, out on the outer sides of both of those. Let's rewrite this thing. 105 kPa times 50.0 liters over 286.7 K equals 75.3 kPa times V2 over 750 K. Well, to get V2 by itself, I need to, this is on the bottom of the fraction, so I need to multiply by this, but have it on the top of a fraction, 750 K. I need to get rid of this. Since it's on the top of a fraction, I need it on the bottom of a fraction. So I'll put it on the bottom of this same one, 75.3 kPa. Now, whatever I do to this side mathematically, I have to do this side. So if I multiply this side of the equation by this, then I must multiply this side of the equation by the same thing. 750 K over 75.3 kPa. Now we can simplify. Since I've got this on the top and this on the bottom, they're exactly the same thing. They can cancel out completely. Since I've got 750 K on the bottom here, 750 K on the top here, those can cancel out. And we've managed to get our unknown all by itself. Okay, that's what we want to do. On the other side of the equation, we have some units of measurement we can cancel. Kelvin and kPa. We are left then with the units that are called liters, and you should know liters measures volume, so we probably set this equation up correctly. We're ready to do the math. It's 750 times 105 times 50, 50.0. Now before we start doing the stuff on the bottom, we're going to hit our enter or equals key. I get a really long number here, 750 times 105 times 50, and we get a really long number here. But now we're going to take and we'll hit a divide button to divide by this first number here on the bottom, 75.3, and hit enter. Okay, got a really long number. Now we're going to divide by this. We're going to hit divide. Now we've hit enter and gotten this. Now we're going to divide now that new number by this number on the bottom, 286.7, and we get 182.3886873. The units of measurement we have left in the problem that we haven't canceled is liters. That equals volume 2. We need to find the correct number of significant digits. Let's see, this originally had a decimal place up here. I added one to it. Said we're going to add a decimal place in here. So this has actually 3 significant digits. This has 3 digits. This has 3 significant digits. This one has 3, and this one has 4. We want the number, the measured or calculated number with the least number of digits, and that's everything but this one, and that's 3. So now we need to round off our final answer to 3. 1, 2, 3. Underline everything else. Draw an arrow to show a rounding off, and we get 182 liters equals V2, and that's our final answer. Okay? Again, all we did was to make a list of knowns and unknowns, choose the right equation to fit those knowns and unknowns, plug in the values, solve to isolate the unknown, or first we isolated the unknown by putting the inverses over here. Then we multiplied everything out, and then finally we did the final answer. Okay? So now I'm going to give you a problem to solve. This is like a good one right here. At what pressure in atmospheres will a gas sample occupy 30 liters with a temperature of 273 K? If it occupies 50.0 liters at 13.5 degrees C and 105 kPa. So Read the problem carefully. You're going to have to be able to interpret math problems on a test. Okay? I'm not going to give you numbers and say this is this value and this is this variable, that variable, and that variable. You're going to have to figure out what variables belong there and where it fits. You've got to do some thinking, use some thinking skills here. If you read this, it says that we started out with everything having these values, and we ended up with this value, but we want to know what the pressure is going to be. Okay? Now the pressure, it says, has to be in atmospheres. There's a little word of warning. This is in kPa. So before you can solve this problem, you've got to put this value, you've got to change this or convert this value from kPa into atmospheres. Remember in that earlier problem we did, we showed that this is the equality statement for atmospheres and kPa. If you have an equality statement, you can build a conversion unit. You build a conversion unit to convert 105 kPa into atmospheres. And the red flag should have gone up for you when you saw your temperature in degrees C. You've got to convert it into Kelvin. So you have to add 273.15 to this to get the Kelvin temperature to solve this problem, because no gas law problem can be solved using temperature in degrees C. And on your test references, there's the conversion right there between Kelvin and degrees C. Adding 273.15 to the degree C to get Kelvin. Now you can solve this problem.